that's the general formula for I, but we can't integrate things with respect to mass, like that just doesn't work, and so we have to find a suitable replacement for dm, and we do that by using density. Since this is a density of a 3D object, being a solid cylinder, then we need to use m over v equals density, of course, and density of a segment would be d little m, because again it's a segment, so it's just an infinitesimally small part of the whole mass, over dv, like that. Now the density of the whole thing would be mass over pi r squared h. That should be big R, actually, because it's r of the whole cylinder, so that should be a bigger R. And then rho seg would be dm over the derivative of this with respect to little r, so it would be little r, because again it's the radius of a segment, it's not the whole thing. H, and then dr here. Pi and h are just constants, so they stay there. You just bring the two to the front to differentiate the little r here. And since density throughout any part of a shape, whether it be the whole thing or a segment of it, is the same, then we can set these two equal. So pi big R squared h dm over 2 pi r h dr. And then we can just isolate for dm. So that almost wrote a dm there. Dang. The pi's cancel, the h's cancel, and so dm equals 2m r dr little r d little r over r squared. Now, since we have a substitute for dm using terms that we can figure out, substitute that in for here. So I equals the integral of r squared, and then times 2m little r dr over r squared. 2m and r squared on the bottom here are constants, so we can pull that to the front of the integral. So 2m over r squared integral of r cubed, because there's an r here, so they multiply with each other, dr. Then we just integrate that like normal over r squared times r to the fourth over 4, with bounds from 0 to big R, because we want, of course, the volume of the whole thing. So that would be 0 to big R, right, instead of little r. That would be what we're plugging in. And so when we work that out, we get that, right? And so that equals 2m r to the fourth over 4r squared. 4 r's over here, 2 r's down here, so all of these cancel and that 4 cancels, and so we get 2m r squared over 4, and that equals 1/2 mr squared. Now, magnitude of the angular acceleration of the cylinder. Okay, so let's see. Part B. So what we know is that net torque, sigma tau, equals I alpha, alpha being angular acceleration, I being, well, this, and sigma tau being torque. And so the block is hanging by a string onto the disc, and so the only force that's acting on that right now for torque would be the string. And so we can set up the equation for that. m1g minus t equals m1a. And then after that, we know M1 is 3. So we get that. And then what we can do, since we know the radius, then we can just plug that in. So the radius of the solid cylinder is 0.3 meters, and then just multiply that by the force that's causing torque, which would be the tension. Set that equal to I alpha. What we can do here is we can rearrange the equation so we get T in terms of G and A, or M1, G, and A, I guess. And so it's 3G minus 3A equals 3 times G minus A, because M1 is 3. And so what we can do there is we can sub it in for this. 3G minus A equals I alpha. Now, why don't we go ahead and just calculate this I value to get it out of the way, since we know the formula for this, of course. So 0.5, mass of the pulley is, or mass of the disc, cylinder is 30, radius is 0.3, 1.35, so 0.3 G minus A equals 1.35 alpha. Now we know that A, linear acceleration, equals R alpha, so we can just sub that in here, 0.3. And again, we know that R is 0.3 meters, so we can just do that. We can distribute the 0.3, so 0.9 G minus 0.27 alpha equals 1.35 alpha. So 0.9 G equals 1.62 alpha. And so 0.9 and so alpha, the angular acceleration of the cylinder, is 5.444 rads per second squared. Yeah. And then another paper for this. Or actually, no, let's use this backside. Linear acceleration of M1. Okay. What we can do for this is to simply convert 5.44 rads per second squared into our linear acceleration, because the only thing that is causing the linear acceleration of the block would be the spinning of the cylinder. And so since we know linear acceleration equals the radius times the angular acceleration, then all we need to do is multiply 5.444 by 0.3, which is the radius of the solid cylinder, and we get linear acceleration of the block equals 1.633 meters per second squared. All right. Part D. Determine the number of revolutions made by the cylinder after 5 seconds. Okay. So what we can do here is use angular kinematics, or rotational kinematics. Omega F equals alpha T, because there's no omega I, because the system starts from rest. And omega F squared, again, no omega I, so 2 alpha delta theta. Now, we know the angular acceleration of the cylinder is 5.444, and then plug in 5 for T. And so omega F equals 27.222 rads per second. Plug that in here. So square it, and you get 741.049 equals 2 alpha, which is 5.444 4 delta theta, and then just find out what delta theta is. Delta theta equals 68.055 radians. And so we want to know that because we want to find out how many revs the cylinder makes and by 5 seconds. And so we can just divide that by 2 pi, because there are 2 pi radians in every revolution. And so if we divide the number of radians by how many radians there are in one revolution, we should get the amount of revs, and that is 10.831 revs at 5 seconds. All right, part E, magnitude of the new angular acceleration of the cylinder after a second mass of 2 kg is added. So what we know is M1 equals 3 kg, M2 equals 2 kg. R, big R, for radius of the cylinder is 0.3 meters, and little r for radius of the axle is 0.03 meters. So now that we have introduced a new block to the system, we will have to analyze the forces for each of those blocks, and we will take the line of motion of M1 as positive. So 3g minus t1 equals 3a, because M1 is 3, and t2 minus 2g equals 2a, because again, the clockwise torque would be considered positive here. And so, yeah, that's the way it is. Now, we know that a equals r alpha. We know also that since they're on the same rigid body, they will have the same angular acceleration. But clearly, they do not have the same radii, so their a's will be different, their linear accelerations will be different, so we have to put subscripts for that. And then we can solve for each of the tensions. And then just... All right. Now that we've done that, we can just use sigma tau equals I alpha, net torque equals I alpha, and simply plug in all of our radii and our tensions, because the tensions are what is causing the torque on this system, and then figure out alpha from there. So 0.3 for big R over here. Again, counterclockwise torque would be considered positive, and so we're going to put M1 first, plug in T1, and then a little r for the radius of the axle, 0.03, equals I alpha. Now again, they will have different linear accelerations, and obviously we don't want that in our equation, so we will have to sub those in for r alpha, because we know that their angular accelerations will be the same. Plus g, like so. And then we can just distribute all terms. Alpha. No. 0.9g minus 0.27 alpha minus 0.06g minus 0.0018 alpha. There we go. Equals I alpha. Just get rid of that. And then we can just group our like terms. And then our I is going to be the same, so 1/2 30 0.3 squared 1.35 g minus 0.06 equals 1.35 plus 0.27 plus 0.0018 alpha. And then we can just calculate that out. 35 plus 0.27 plus 0.008. Alpha equals 5.056 rads per second squared. Alright, part F, new linear acceleration of m1. Don't know why I put an equal sign there. So again, we know that a linear acceleration equals r alpha, and again, they're on the same rigid body, so their angular acceleration will just be this, and their radii are different, and so we're going to use big R for this one. So a1 equals 0.3 times 5.076. A1 equals 1.523 meters per second squared. Part G, kinetic energy. All right, so what we can do is we can find the velocity of m1 when it has fallen a distance equal to 5r, 5 big R, and big R is 0.3, so that's going to be 1.5 meters. And then we just plug this in for x here, so VF1 squared equals 2, and then our linear acceleration is, of course, 1.523, 1.5. And then square root it. So VF1 equals 2.137 meters per second. And what we can do from here is find omega F1 by using this relationship, V equals R omega, and so omega equals V over R. And so just divide this by R, which is 0.3, for block 1, 7.124 rads per second. And then we can plug that in to the rotational kinetic energy equation, Ke rod, of the cylinder, which is 1/2 I omega squared. I, of course, being 1.35, 7.124 squared. Equals 34.262 joules. And then net work done on the system after 5 seconds. So we can use the work energy theorem, which says net work equals change in kinetic energy. And since the whole system starts from rest, then we don't have to worry about any initial kinetic energy, and so we can just use the kinetic energy at 5 seconds for each object. So Ke ln 1 for object 1 plus Ke ln 2 for object 2 plus Ke rot for the cylinder. And that will equal our net work at that point. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 I omega squared. So all we need to do now is just find all of those velocities and then plug it in, and we're good. So we can use kinematics. V1 equals A1t, right? Since there's no initial velocity, so we don't need to worry about a VI here. That should be VF1. And then A1 is 1.523 meters per second squared. Multiply that by 5 seconds. VF1 equals 7.614 meters per second. VF2 equals A2T. A2 we can just find by using, again, A equals R alpha. Little r this time because mass 2 is attached to the axle, so A2 equals 0.03 times the angular acceleration of the cylinder, which was 5.06 mass per second. 0.076 0.03 5.076. So A2 equals 0.152 rads per meters per second squared. Dang it. And then we can just multiply that by 5. So VF2 equals 0.761 meters per second. And then for omega f of the solid cylinder at 5 seconds, we can just do alpha t. So alpha, again, was 5.076. And then multiply that by 5. 25.379 rads per second. All right, so we can just plug all of these values into this equation. Okay, this was the equation. Change in KE equals KE ln plus KE ln 2 plus KE rho 1/2 M1 V1 squared plus 1/2 M2 V2 squared plus 1/2 I omega squared. And since we already found all the velocities, we can just plug them into the equation here. And we get 522.304 joules for the kinetic energy of the whole system at the end of 5 seconds, which is equal to the net work done at that point because there's no initial kinetic energy.